everyone, and welcome to this episode of Foundry Fireside. My name is Grace, and I am an intern on the Foundry Communications team. I'm here today with Ambarneil Saha, a postdoc working with Peter Urshus at the National Center for Electron Microscopy. Thank you for joining us, Ambarneil. Can you start off by telling us about yourself and what you do at the Foundry?
Thank you for having me. I work on a technique called scanning transmission electron microscopy, or STEM, which encompasses essentially three major modalities: imaging, diffraction, and spectroscopy. I specialize mostly in the latter two, but on a more abstract level, you can basically think of me as a nanoscale photographer, or I guess videographer even. So the way STEM works is by generating a focused beam of high energy electrons forcibly propagated through a potential drop of typically, let's say, 300 kilovolts. And thanks to wave particle duality, you could think of these electrons simultaneously, both as tiny billiard balls or as particles, but also as waves. And their corresponding wavelength is around 2 picometers. So that is the underlying reason why I can take photos or videos of atoms or crystals at the nanoscale. So that's, for instance, many orders of magnitude smaller than the width of a human hair. Because if you want to experimentally measure nanoscale phenomena, you essentially have to use a probe, which is in and of itself also small enough, granular enough, sensitive enough to detect those objects. So basically, the length scale of your probe should either be commensurate with or smaller than the object you're trying to analyze. So the analogy I usually give here involves Braille dots, which can actually have very stringent regulations surrounding, for instance, how they're embossed, the spacing between them, level of protrusion from the page, stuff like that. All of that is actually very carefully optimized for maximum readability, legibility, for the friction ridges of your thumb, your fingers essentially. But you can imagine a situation where you were, let's say, trying to read progressively smaller and smaller and smaller Braille dots. You would ultimately get to the point where you could barely feel them anymore with your thumb or with your finger or whatever, right? So they would essentially eclipse the limits of tactile perception. And that's a great example of a mismatch between the size of your probe, which is now too big, too crude, your finger is too crude to detect our magically shrinking Braille dots. So unlike, for instance, optical microscopy, which you may have heard of using visible light, whose wavelength is much, much longer on the scale of hundreds of nanometers, STEM, or scanning transmission electron microscopy, uses a very, very tiny 2 picometer probe. And that is what empowers us to see those objects at the nanoscale.
Wow, that sounds interesting. I know you work specifically on radiation damage. What drew you into that?
Sure, exactly. So all this incredible nanoscale information, unfortunately, does not come for free. We pay a very, very steep price for it. And that is because, well, turns out if you bombard, especially organic matter, with relativistic electrons accelerated to 70% the speed of light, you also end up simultaneously inflicting irreparable damage to your specimen. So basically, we're always perpetually in this race against time to extract whatever information we're interested in before the sample itself is totally destroyed by the very, very powerful ionizing beta radiation we're delivering inside the microscope. So take, for example, one of the three modalities I mentioned earlier, diffraction, which is kind of where I got started. Diffraction is, briefly, a very specific type of interference pattern formed when our incident electrons impinge on a crystal lattice, whose periodicity or spacing is usually on the scale of angstroms. So again, that's matching, or in this case, actually a bit bigger than the wavelength of our probe. And to record and observe a diffraction pattern, essentially, we're specifically trying to leverage a form of scattering called coherent elastic Bragg scattering. So all that means is as the electrons hit atoms within the sample, there's actually a myriad of different types of scattering events they can undergo. And unfortunately, only a relatively small fraction of those scattering events contribute, quote unquote, productively to the signal we measure in a diffraction pattern, for instance. And those elastic events essentially don't damage the specimen. However, many other scattering events involve inelastic collisions where some fraction of the incident electron's energy is transferred to the sample. It's deposited within the sample. And using a technique called electron energy loss spectroscopy, or EELS, great acronym, we can actually spectrally resolve that distribution of inelastically scattered electrons. So you can do that in terms of how much energy they've lost. So for instance, let's say our incident electron goes in, impinges on our material with energy 300 keV, but comes out with energy 300 keV minus some number, let's say 22 eV. So it turns out that 22 eV energy loss is actually 4 or 5 times greater than the BDFE, the bond dissociation free energy of a carbon-carbon covalent bond. So the bonds in any organic specimen can easily break and generate all kinds of reactive species as byproducts of exposure to ionizing radiation, such as, for instance, free radicals. Now, many of these can then diffuse away from the parent bond after it's broken and begin to wreak havoc elsewhere in the specimen. And this phenomenon broadly is known as electron beam induced radiolysis. And broadly speaking, we can call that radiation damage. So, what I work on is developing a mechanistic understanding of how radiation damage works. So ultimately, we can develop strategies to mitigate it, to basically buy ourselves a little bit more time to extract all this incredibly rich information from these organic specimens before they're ultimately destroyed.
Okay, so then in your most recent paper on showing radiation damage during electron microscopy, what surprised you the most?
Sure. So in that work, we used a technique called 4D STEM, or scanning nanobeam electron diffraction. And this is a bit difficult to explain verbally, but basically what it involves is raster scanning, in my case, a nanoscale probe, across some arbitrary region of the sample in what we call real space or direct space where you and I live, partitioned into, let's say, a 512 by 512 grid. And at each point in that grid, we acquire a diffraction pattern. Now, as you can imagine, this actually produces data at this prodigious rate, fairly insane rate. So all of my work is uniquely enabled by a very fast experimental camera we have at NSEM, the 4D camera, which has an 87 kilohertz readout time, corresponding to around 11 microseconds. So we ultimately end up producing data at very, very rapid clip of around 480 GB per second. You can imagine that really fills up a hard drive pretty fast. So my advisor, Peter Urshus, led this Herculean effort to produce something called a sparsification pipeline involving the DOE NERSC supercomputer at LBL. And, since I'm trying to analyze radiation damage, right, I'm basically acquiring many, many consecutive scans of the same sample. A 512 by 512 scan, the raw size is 174 GB. A 1K by 1K is 696 GB. So, not exactly lightweight. You can maybe fit a couple of those onto your laptop. And well, the sparsification pipeline, what it lets us do is we can basically perform a nearly lossless compression of that raw data down to a sparsified HDF5 file, only tens or hundreds of megabytes in size. And we can visualize that in this software that we developed, which we call DUSK, short for Dual Space Crystallography Explorer. And so let me quickly pull up a demo of that. So on the left-hand side, essentially what you're seeing is a rendition of real space. So we see lacy carbon support, and this rectangular prismatic object over here is an organic crystal of interest. And these two squares, both on the left-hand side and the right-hand side, correspond to virtual apertures. And they're customizably shaped, which gives us tremendous power in terms of essentially which regions we want to selectively extract signal from. So I can take this box in real space, for instance, and if I just make it smaller, now we're exclusively looking at amorphous signal from the lacy carbon support. You can see all those beautiful spots in my diffraction pattern suddenly disappeared, indicating that all the material within this real space box now is simply amorphous, has no long-range periodicity or lattice or any kind of long-range order. Now, if I take that crystal over here and I move my box like this, and instead I raster the box over the crystal, you can see once again we've regenerated our gorgeous diffraction pattern. And also we're observing quite a bit of internal rotational misorientation, or classically what's called mosaicity, within this particular crystal. Because as you can see, the orientation of that diffraction pattern is definitely changing. You're seeing different spots essentially coming in and out of what we would call the Bragg condition. Now, the beauty of 4D STEM and why it's so powerful is that I can also conduct this exact same analysis in reverse. So notice how I have not yet touched this very tantalizing reciprocal space box over here. I can make that smaller as well. And if I put that over one particular Bragg reflection, one particular spot, as I just did, notice how one specific area essentially lit up in real space. So now what I've done essentially is I've isolated exactly which coherently diffracting domain contributed to produce that particular Bragg reflection in reciprocal space. And so what we essentially did is we exported that diffraction pattern from the entirety of the crystal, and we parked one particular virtual aperture over this reflection, which you're seeing here enclosed in that orange square. And we tracked how the corresponding coherently diffracting domain decayed as a function of exposure to accumulating ionizing radiation. So as I play this video, what you'll notice is that this particular coherently diffracting domain, to our surprise, actually unfurled into a larger striation after the initial scan, suggesting that there is internal rearrangement happening within the molecular lattice. And if I just let this finish, we ultimately see we've succumbed to the ultimate fate of all CDDs, which is, of course, monotonic decay and death. But en route to ultimately getting destroyed, we saw it unfurl into a larger striation because of some internal rearrangement induced by electron beam-induced radiolysis. We were able to image that simultaneously in both real space and diffraction space using 4D STEM.
And during that project, what surprised you the most?
Great question. So we also tried, in retrospect, kind of a left field experiment where we parked our probe at one particular dwell point on the crystal for an extra 200 milliseconds in between consecutive 4D STEM scans, essentially producing a localized region on the crystal which had endured far more ionizing radiation than the rest of it. And what we observed is this. We observed from that dwell point a tide of amorphization radially propagating outwards, which you can see right here as I'm reconstructing the signal from, again, that particular Bragg reflection enclosed within the orange square. So what we realized, and this was highly unexpected, is that we're essentially watching the progression of some kind of reactive species produced by radiolysis. We're watching the outward spread, this frontier of amorphization coming radially from that particular region. And so we think that we've done lots of experiments, follow-up experiments mechanistically to try and figure out what the identity of that species is. But at this point, we're fairly confident that as a result of electron beam-induced radiolysis, we've produced some kind of low molecular weight radical species. And what we're essentially seeing is that that hydrogen radical, or some kind of species like that, can diffuse away from that dwell point and create what we called an expanding impact crater in the paper. And so we're currently working on many, many ways to use this as a mechanistic probe in many other types of systems to kind of figure out what's going on there as well. So you can imagine making specific chemical modifications to our sample and then trying the impact crater technique, using it as an assay for radiolysis, in other words, and seeing whether we can affect the rate at which the crater expands by making, again, specific modifications and seeing how that affects the overall susceptibility to electron beam-induced radiolytic damage. So this was a totally unexpected result and actually occurred somewhat serendipitously, but I guess that's how basic science works, right? That's how basic curiosity-driven science often works, right? You see these kinds of results, even though you didn't expect them. And ironically, this ended up being one of the key results that produced, I would say, almost like 7 or 8 branching side projects. So it's one that, in retrospect, I'm very fond of.
Oh, that's really cool. Before we go, do you have any last comments or any piece of advice that you would give to aspiring scientists?
Sure. Advice for aspiring scientists. Interesting. I would say, well, first of all, hang in there. Now is frankly kind of a uniquely difficult time to be a first year grad student. But more generally, I would say read widely, read voraciously, read outside your field. You know, the scientific literature is so vast, but one kind of consistent engine of scientific progress, which I've definitely seen in my career so far, is forging connections between like seemingly disparate fields. So maybe there's some technique that's been gestating in field X, but it actually has some much more impactful application in field Y. And no one's just thought about that before because, well, the right pair of eyes hasn't quite seen it yet. That could be you. I would say also never be afraid to ask quote unquote dumb questions. I think as you get older, maybe sometimes you can start to quietly accumulate more inhibitions. People just sort of expect you to know stuff. When you're younger, youth kind of empowers you to ask very sort of broad quote unquote dumb questions. But in many ways, I've seen maybe a lot of older folks in the room would want to ask those questions, but they feel a little bit too inhibited. And those questions often, like, why are we doing this experiment again? What does this technique do? How does this contribute to the overall narrative? Those can sometimes drive a project forward. Uh, so I'd also say, in addition to reading, practice writing as well. Expand your vocabulary. Uh, Writing a paper is honestly very, very difficult. Diversify your syntax, sentence structure, stuff like that. Learning how to weave a coherent narrative out of very complicated threads of data is really an art, and it ain't easy. So you just really have to practice that. And finally, I guess I would say don't be afraid to cold email people. It's something I do all the time. Virtually all scientists love talking about their work if approached properly. But so if some other dude on the side, on some other side of the planet, developed a piece of software that you're struggling with, just contact them directly. It's almost always the fastest way off the struggle bus, and other humans know stuff, and most of the time they'd actually be happy to share what they know or even start a collaboration. Now, I will say some degree of fumbling around in the dark is occasionally pedagogically useful, but a critical part of maturity as a scientist is sort of recognizing when you're getting diminishing returns by struggling by yourself. So know those limits, and once you've reached them, never be afraid to ask for help. Never be afraid to even just contact random people.
Yeah, thank you for that. Okay, so that's all the questions I have for today. Thank you so much for joining me. It was really great to learn about your research. For those of you who are watching, if you're interested in learning about what goes on at the Molecular Foundry, please stay tuned for more episodes of Foundry Fireside.